in the year 1400 versus the way they do things in the year 1500 probably is not much different. And I'm still using the same hole, for working the field, right? As my grandfather or something. But then if you project in the future, like only 20 years from now, which is about one generation, I would bet you that things will be very different. Technology will be completely different.
Right.
Yeah,
But that also indirectly affect how people look at other things.
Or what they even consider technology to be back then. Way different than it is
Yep.
now.
Well, they're talking about the development paralysis, where like you're trying. There's so many new languages and libraries and system files that are coming online that they can't. Like developers can't. Like people that want to learn or COBOL, or not COBOL, but Python and C and Java are being kind of like, well, am I learning this or am I going to learn this new, AI interface,
Something that when you become a programmer is really important.
When I eventually get children, like you can have like so many things that they don't even know, like the Nintendo 64, or it's like old generation gaming. Like,
oh yeah.
Like what's a Nintendo 64?
I still don't understand the console naming. Like, how do you go from Xbox 360 to Xbox One? Somebody explain this to me.
I think it's.
This is the name.
There's no major difference between
Yeah, but
that
naming
and
conventions
something like Call of Duty as opposed to like original Super Mario Brothers and something unique.
Yeah.
Like, don't you think that the next sort of stage of video games is going to be something much more immersive? It's still the
virtual
time.
reality.
But also like more integrating of just peripheral things like still mentality thing, or system like time tracking, but
Oh, when you actually
And
feel
it looks like you're watching it.
that's virtual reality.
yeah,
As much as I hate this, my husband
virtual reality is like you're immersed into the environment. And I'm still thinking like you still have the screen in front of you, and you know you're not in
depending on what
the
system it
real
is
world.
on, I'm like, are you watching something? What are you doing in here?
Yeah, it's like, well, they're saying that like the Oculus Rift is repatterning people's brains now, to where they're like getting, like if you walk over a cliff in the Oculus Rift, your brain,
Thinks you're walking over.
yeah, it can't, it's starting to like not be able to interpret the difference. So your anxiety and blood pressure will go up, and your muscles will like react as if you're about to fall.
So you should probably have a doctor on site.
All right.
I mean, but it's virtual reality, and it's like it's not that.
All right, so we are going to have to get started. I know you guys are engaged in something that's related to computer science and is very interesting, but we still have to get started because I need to give you guys the solution to sort for. There's no new homework assignment as of yet, okay? But we have to kind of continue to talk about how to read numbers from a file and then move on to pointers and address of something. So we do have quite a few things that we have to go over today, and we'll start with this one. So sort for is already due, and what I'll do today is to give you the solution, or one of the many ways to solve this problem. I already downloaded the file, so I will start using the same starting point that you guys start with, and try to derive the solution for this particular homework assignment. All right. So your code is supposed to go here, and the job is to sort the values in variables w, x, y, and z, so that you end up with w being the least, z being the largest, and my code will take care of the printing part. Awesome. All right. So what we'll do is we'll borrow code from the find max program. So we'll still use the logic to find the maximum of the 4 variables, except when we find it, we don't assign it to max, the variable. We'll exchange it with z in this case. Because z is supposed to be the largest to begin with, so we'll just go ahead and say, oh, okay, this value has the largest value, so we should exchange it with z, unless it is z already. So one way to find the largest of the 4 variables is just to compare, right? We'll say, okay, if w is greater than or equal to x, and w is greater than or equal to y, and w is greater than or equal to z, then we'll go ahead and do the following. If not, we'll do some additional comparison. So if w is not a maximum, then we only have 3 variables left. we have x, y, and z left as potential maximums. So in that case, I have to say, okay, is x the maximum of those three? If x is greater than or equal to y, and x is greater than or equal to z, then we'll perform whatever we have to perform when x is the maximum. If x is not the maximum, then we have two variables left as potential maximums. We have y and z as our potentials. So in this case, we have to check those two. But since there are only two, one comparison is all that I need. So in this case, I will check. I'll do the reverse. Instead of confirming the, suppose I can do it the other way. So I will check, compare y to z, and ask is y greater than or equal to z. If so, we'll do it like this. If not, there's actually nothing to do, but we'll leave some spot here. We'll leave a spot there. The reason why I wrote the else if like this is because the indentation of this program actually indicates the correct nesting of the statements. C and C++, unlike some other programming languages, they do not have else if as a concept. Okay, but you can kind of say if after an else, but the effect of that is not that this is a multi-branch conditional statement. It is actually a nested conditional statement. When the compiler parses else, it is expecting a single statement after that. So in this case, it is expecting a single statement, and that single statement turned out to be this entire conditional statement. When the compiler encounters this particular else statement, it is also expecting a single statement, and that single statement turned out to be this particular conditional statement. When the compiler encounters this else statement, it is encountering this empty block statement. So that's why I use indentation the way I do here, and put an indentation here and two more indentation over here, because these conditional statements are actually nested within the other conditional statements. Right. So getting back to where we need to do when we confirm who is the maximum of the 4 in this case is w. So we can now repeat this sequence of operation and exchange the value of w with the value of z. So this part should not be really surprising at this point, because we talked about this in the practice exam, the mock exam for exam 1. And I can just go ahead and copy and paste it over here, except in this case we are confirming that x is the maximum, so we'll be exchanging the value of x with the value of z. And over here we're confirming that y is the maximum, so we'll be exchanging the value of y with the value of z. Alright, this is not the entire program, it's not the entire solution, but it does get something done. This code is supposed to find the maximum and then exchange the value of whoever has the maximum, or with whoever is supposed to store the maximum. So at this point, I will stop the program, I will stop developing the program and test it, okay? Because it doesn't make any sense for me to write any additional code unless I know this part is working already, because the rest of the program depends on this part. So I will exit the editor and then use G++ to compile the program with warn all and pedantic options. Specify the output that we just made, and then the input is main.cpp. I don't have any compiler errors, so let's go ahead and check it out. So I will only give it a few test cases to see whether it works or not. So I'll give it like 4, 2, 3, 1. And what do you think should be the output when the input is 4, 2, 3, 1? The output would be 1, 2, 3, 4. Okay, so it would appear to be completely sorted, because it will exchange the value of the 4 with the value of the 1. And that's the output. Okay, let's check something else. Let's try 2, 4, 3, 1. And in this case, what would be the output?
2, 1, 3, 4.
2, 1,
3, 4.
2, 1, 3, 4 is correct, because the 4 will exchange with the 1 also in this case. Okay, and it's 2, 1, 3, 4, just as expected. So I'll give it one last test case, just to make sure that it doesn't screw up on the obvious one. Okay. Are there any questions with the program at this point, or does anyone want to throw an additional test case at the program?
2, 2, 3, 3.
2, 2, 3, 3. Okay. So with 2, 2, 3, 3, it really should not do anything, because out of the 4 numbers, 3 is already the maximum, so it will leave it alone. Of the 3 remaining, 3 is already the maximum, so it will leave it alone. Of the 2 remaining, it will actually do the swap, but swapping 2 with 2 is not visible because they have the same value. So the output of this particular invocation should be 2, 2, 3, 3, all just like that. That's exactly what we got.
What about 2, 3, 2, 3?
2, 3, 2, 3. Okay, so let's try 2, 3, 2, 3. So out of 2, 3, 2, 3, I actually misspoke because we only find the maximum and exchange it. So in this case, the maximum is 3 because I'm using greater than or equal to. So it will confirm that x in this case is the maximum, and it will exchange it with z. But since x and z actually have the same value, the exchange takes place, but it doesn't have any actual effect because they are of the same value to begin with. So in this case, the output should be 2, 3, 2, 3 with no changes. Okay, so that's how we can test the program and make sure that at least this part works. So now that we know this part works, we can go back into the program and say, well, since we can now take care of the largest value, what about the other 3? What can we do about the other 3 to get them sorted? Well, if I can find the maximum out of 4 variables and make sure that the maximum is the last one, I can probably do the same thing with 3. So what I'll do is I'm going to look at this code and say, do I have the structure to find the maximum out of 3 and then exchange the largest value of 3 variables with the one that is supposed to have the largest value? And we already have the structure. This part will do it. The variables are wrong, okay, but the structure is right. So what I'll do is I'm going to use a feature in VI and just say copy line 48 to line 59 to here. Oh, nope, take it back. 48 to 59, copy to this point. So now I have a copy of that code, but the indentation is wrong, so I'm going to fix the indentation. The indentation is from, I have to set up the shift width to 2, and then we specify from line 41 to line 61 to line 73. Shift everything to the left-hand side once. So that's how I can adjust, the indentation with only one, command. Okay, so now we can come in and say, okay, this code is not right because we don't have z to consider anymore. Whatever is in z is the maximum, so that part is already done. We only have w, x, and y to consider now, and we want to find the maximum and put it into exchange that value with the value of y. That's not too hard. Z is no longer needed, so we'll just replace z with w in the comparison. But in this case, since we're confirming that x is the largest of the 3, we'll exchange the value of x with the value of y. Same thing over here. If y is greater than w, then y is the larger of the 2, so we'll exchange that with w. And that's it. That should put the second largest value into y. The first 2 can still be unsorted, but the last 2 values should be sorted, and they should have the largest and the second largest value. So let's go ahead and give it a try. So we recompile the program, rerun the program, and let's give it some value to test with. So we can test with like 4, 2, 3, 1, and it comes back at 3, 2, 1, 4, which is incorrect, okay, because it is not exchanging with the right place. So let's go back and check on the code because I made a mistake somewhere. Okay, x is the largest, we have to exchange it with y, and then y is the largest. Oh, that should be the other way around. If w is the largest, then we'll exchange it with y, not the other way around. Okay, so there we go. We had a little problem.
Aren't you gonna have to rearrange the exchange operation as well?
No, the exchange I don't have to.
Oh, because
I just
do it
have,
either way.
Yeah, because exchanging y with w as opposed to exchanging w with y would do exactly the same thing. Okay, so let's go ahead and test retest the same test case. Now this is called regression testing. Regression testing means if you found that your program failed on one particular test, then you remember that particular test case and you retest using that test case thereafter, okay, or until it's not applicable. Okay, so since we knew that this program did not work with this particular test case, we'll retry the same test case, and this time it worked out correctly. Okay. Anything else you guys want to try out with this one? What about 2, 1, 3, 4? Now, if you look at 2, 1, 3, 4, the last two variables have the largest and the second largest values already. So no exchange should take place in this case. Okay, because each one is already in the right place. So 2, 1, 3, 4 should have the output of exactly just 2, 1, 3, 4, and that's exactly what happens. Okay. So now that I have a pretty good idea of this part is working, we have to work on the last part. The last part means out of the two variables, W and X, I want to make sure that the larger one is in X and the smaller one is in W. So what we'll do is we'll just kind of copy these 4 lines, stash it here, adjust the indentation, just so that the indentation still indicates the structure of the program. And this time it's just between X and W. So we have X and W here. And if the comparison is true, if the expression is true, then X is in the wrong variable. We have to exchange the values of X and W to fix it. And that should be it. So once again, I save the program and recompile the program. Rerun it. And we can give it 2, 1, 3, 4 just like before. Space. And it's not sorted. I think I might have forgotten to save the file. Let me check. If X is greater than or W, oh, I got it flipped. I'm sorry. If W is greater than or equal to X, which means it's out of order, then we swap it. If it's already in order, we don't want to swap. That's why it didn't work before. Okay. Recompile, rerun the test case, and this time it works on those two numbers. Are there any questions about the solution? Is it kind of how you do it too? The comparison order may be slightly different, but is that generally speaking how you solve this particular problem? More or less? Okay. Did anyone try to use like a big, huge ternary operator to do it?
I use a ternary.
Huh?
I use the ternary operator.
You use a ternary operator? It gets a little bit harder with this one, just to use the, because you need the exchange. Did you use an additional variable?
No, but it still worked.
Interesting.
Yeah, you can get it to work. I turned it in different, and then I did a ternary just so I could do it. It works.
Okay. All right. Well, when I grade it, I will, I'll take a look at your solutions and see how you guys come up with a solution. So that's it for the homework assignment. And after that, we now focus on input and output using files. And today we're moving on to scanf. So scanf is this particular portion. This is what we talked about last time, how to print a value using base 10 and base 16 and stuff like that. I'll just kind of give you a preview of, not preview, but a review of what we talked about last time. So last time we talked about how to print a number. Like if I want to print the value of I as a decimal number and as a hexadecimal number using printf, this is the way printf works. This is called a format string. The format string for the most part is printed verbatim. Whatever you specify here is just printed the way it is, except when you have a percent symbol. A percent symbol signifies that this is a placeholder. So in this case, the placeholder called %d is specifying the place of a number that should be printed as a signed base 10 number. When you have %x, it is a placeholder for a hexadecimal number. So when you have placeholders inside the format string, you have to have a matching number of values to match the placeholders. So in this case, the first I is matching the first placeholder of %d. The second I is matching the placeholder of %x. So that's how we use printf before we had the first exam. Now that we are done with printf, we have to kind of do the reverse and find out, how do we, instead of how to print something, how do we read something from the standard input file? And by the way, when you use printf, it is implicit that you're printing to the standard output file. Okay, printf does not work with any other files, just standard output file. So what we're doing now is we are, going back to this part. We are now proceeding with getting input from a file using scanf. All right. So scanf is, as the name implies, is a counterpart of printf. Which means scan is scan formatted, and it accepts pretty much the same format string. If you want to read a base 10 signed number, then you use %d to specify, oh, this is what I'm trying to read. But there's one major difference. Let's take a look at this program and figure out what it is supposed to do. The first line is a #include line, which means it is just including the text, the content of standard io.h as if it is a part of this particular program. All it really is doing is to import what we call the prototype of subroutines into this particular program. So by the time we get to line 6, the compiler knows how to use scanf. And if I do not use scanf in the right way, the compiler can complain about it and go like, oh, this is not the right way to use it. So that's the purpose of line 1. Line 3, line 4, we know that's just the beginning of the main subroutine, and this is the end of the main subroutine. Nothing to it. Int x means we are now declaring an integer x. It's a variable, and all of the fun stuff happens on line 6. So line 6 is a fairly complex line, and we want to figure out what it does. Okay, because that is really part of the focus of today's lecture, is how do we use scanf. So let's take a look at scanf here and try to figure out what it does. Now you can either read the rest of my notes to find out how to use scanf, but scanf being a very popular subroutine that is used in a lot of C++ programs, on most Unix type systems, the man page or the manual page of scanf will actually tell you just about everything that you need to know about scanf. So we want to know a few things. Okay, we want to know what is it that we are passing to scanf as a parameter. What is this part here, and what is that part there? The second question is, it appears that we are comparing the result of scanf with 1. Why do I want to compare with 1? What is the meaning of the return value of scanf? That's the second thing that we want to figure out. And then the other part of the conjunction, which is this part here, we'll worry about it later, okay? Because that part is fairly simple. We know how comparison works, and also how conjunction works. So we're not too concerned about this part. We're just much more concerned about the first part, which is this part here. If you're using any type of Unix or Linux type of environment, you can go to any command prompt and type man scanf to look up the man page of scanf. It may not be installed in some systems because it is actually considered a developer type of topic, but in most Linux systems, if you look up man page to look for scanf, it should pop up a page like this. And this is what we call a man page or manual page in Unix/Linux type of system. And it explains various stuff. If you want to learn how to use CD, you can say man CD and it will teach you how to use CD. But in this case, we are actually looking at the Linux programmer's manual. In other words, we are looking at C subroutines and figuring out how to use a particular subroutine. In this case, we are using scanf, and you can see how scanf, fscanf, sscanf, vscanf, vsscanf, and vfscanf, they all have the same man page because they're all basically variations of each other. In this case, we are particularly interested in this one. There's a lot of description. Okay, I'm not too concerned about the entire description here, so we'll go through all of this stuff. conversions. Okay, so the following type modifier characters can appear in the conversion specifier, and you can basically specify how to interpret the input of standard in. The following conversion specifiers, these are the things that we have seen already. This is the one that I chose to use. Match an optionally signed decimal integer. The next pointer must be a pointer to int. Okay, so this is our first encounter to the concept of a pointer. Okay, it basically says we have a placeholder of %d, but in order to fulfill the placeholder, we now need a pointer to an integer and not just an integer. So we'll talk about how that can be done when we get to the code. But I also want to find out what is the return value. The return value says these functions return the number of input items successfully matched and assigned, which can be fewer than provided for, or even 0 in the event of an early matching failure. Okay, what does that mean? That means when you're using scanf, it's trying to interpret and parse the characters coming in from standard input file, byte by byte, character by character. The way it's interpreting these bytes is based on the format string. Since we use %d, it means scanf understands, okay, I'm looking for a signed decimal integer. Okay. The value returned by scanf is basically how many integers did I actually read? How many did I ask for? Let's go back to the source code and you can tell me how many integers did I ask for in the scanf. How many placeholders are there? There's only one placeholder. And that one single placeholder, which is %d, specifies an integer, a signed base 10 decimal integer. So I was only asking for one thing. I'm asking scanf and say, okay, read the input file and give me an integer. Now, because scanf returns the number of items that was actually parsed entirely correctly, what do you think would be the options for this particular, for the return value of scanf? What can it return? I was only asking for one thing. You guys interpreting my question? No? Okay. So the question is, if you just look at the function called scanf, which is this part here, and based on the documentation that we just read, which is scanf returns the number of items that was parsed correctly, okay? What can be the range of the return value in this case?
1.
It can be 1 because I asked for one integer, right? If it did read one integer, the value returned by scanf will be exactly 1. Can it be anything else? It can be a well, no. Scanf is not going to return a negative number. Scanf is not returning the value that it just read. It's telling me how many things it has read according to my format string.
You're going to get a 0 for null here.
It can be a 0 if it cannot see a number. Okay, so let me just answer the question. Scanf in this case can return a 0 or a 1. If the input file, if the standard input file does not have a base 10 number, like ABCD, okay, that's not a decimal number, it will return a 0. Basically, it's saying, okay, you asked me to read a base 10 integer, I cannot find one. And that's why it will return a 0. If I type 1, 2, and then press the enter key, which can be interpreted as 12 in base 10, then scanf will read that 1, 2 as individual characters, interpret 1, 2 as 12, which is the value 12, and store that value 12 into X in this case, and then return a value of 1 because it has successfully read one item that I asked for. But I was only asking for 1, so 1 is the maximum that scanf can return in this case. Yep.
Sorry. Come back.
Okay. All right. So is that part okay? Does everybody understand why scanf in this particular context can only return a 0 which means I didn't read what you asked me to read. There's no such thing in the input file. Or a 1 if it is just reading, a integer. Yep.
What if you input file had 12 and 24? Would it spit out 2?
No, it would just spit out 1 because the 12 goes first. Now I'm assuming you have either a space or a line feed separating the two numbers, right? So it will read 1, 2, and then it will hit a space or a line feed character, and right at that time, scanf comes back and say, "Oh, you asked me for one, integer. Here it is. I store it into X, and you can do any processing you want in X." Now, if you are in a loop like in this one, if the logic of the loop says we can go back, the second time you call scanf, then it will encounter 24. It will interpret 2, 4 as 24, and then store 24 into X.
So why is it skipping it in the loop? When it's the second time around, why wouldn't it just hit 1, 2 again?
Because you're reading the file sequentially. Remember, an input file is a conveyor belt. You cannot rewind it.
Okay.
Once you process something, once you take something out of the conveyor belt, it is gone.
Okay.
So let me just make sure I understand this then. So the value in the case for the first time around where it picked up 12, the number 12 would be stored in X, but it would return a 1 because it
That
found
is
the
correct.
one integer. Okay.
That is correct. Because it has two. It will do two things.
Okay.
One is to return the number of items that it has read successfully. But since I only asked for 1, that's the maximum it can return is just
Okay.
1.
That makes
The
sense.
second thing it does, which is what we call a side effect, is to store the value into X. Yep.
I don't understand how scanf is only asking for one thing here. Like
It's
how
only-
it's supposed to ask for multiple things.
Because each thing that I ask for has to start with a percent symbol. The percent symbol is kind of like a prefix of a placeholder. So if I only have 1% something, that is the placeholder of only one particular thing that I'm asking for. So in this case, each call to scanf can only return or read one thing, interpret and read one thing at the most. Now, if the input is 1, 2, 3, is ABCD, then they won't even come back with 1 because ABCD cannot be interpreted as a base 10 number. So in that case, it would just come back and return a 0 and say, I cannot read whatever you're asking me to read, sorry. Okay? Okay, now that we understand this part of the program, what about the rest of the program? The rest of line 6? Because line 6 is just one single line, however, it is kind of complex. What does it mean if this entire thing is true? Go ahead.
Going to the while.
Say
I'm
again?
sorry, if it's all true, then on the left side of that and the right side are both true, then it goes to the while.
That's correct. That is what the program is supposed to do. But what is the meaning of this part being true? Just this part.
That's found some of the scan.
It has found what I'm looking for. Okay, it found a base 10 integer, read it, interpreted it, and put the value of that integer into X. Is that okay? Okay. Now that we know what the left-hand side of the conjunction is, tell me about conjunction in C and C++. If one side is false, would I evaluate the other side? If the left-hand side is false, would I evaluate the right-hand side? No. But so under what condition would the right-hand side be evaluated? Only if the left-hand side is true. Okay? So that means this expression here, whether x is different from 0, does not even matter if I did not read the number. Right? It makes sense, right? So if I did not even read a number into x, don't bother to compare it to 0 and just get out, because the first part, the left-hand side, is false already. And in a conjunction, if one side is false, the entire thing is false. Go ahead.
But does 0 count as a base 10 number for scanf?
Well, 0 is a value. It is not base 10 or any base. It's just a value.
Well, I guess what I'm asking is like if the %d, like you put in input 0, does scanf count that as a hit?
Yes.
Okay.
It counted as a hit. It will store the value 0 into X, and then because of the conjunction, it will now evaluate the second side, the right-hand side. Yep.
That's the same thing. So if we give it 0, it's going to say 0 is a decimal, so I'll return 1,
Mm-hmm.
which is true, and then it'll move on to the other side, say 1 is not 0 and then go in for the while?
It will say 1 doesn't. No. It will say 0 is not is different from 0 is false and get out of the
So
loop.
it's the scan.
Because okay.
Gonna do with the Boolean thing, with the 1 or the 0. See how it goes? I'm trying to understand because I'm not.
Okay, scanf returns the number of items that was actually successfully interpreted. That's what it returns. If I ask for multiple things, if I ask like %d, %d, percent space, %d space %d, which means I'm reading two numbers, and I use %x and %y, then it will attempt to read two numbers at the same time. Then it can return 2, 1, or 0, depending on how many numbers were actually specified in the input file. Now, since I'm only asking for one integer, which is %d, it can either have read a single integer or have not read a single integer, so the value can only be 0 or 1. That's what scanf returns. Now, what it stores into X is what the input file specifies. So, when you combine these two, this entire conditional statement or this entire condition is basically saying, first of all, did I read a number? This part is basically just asking, did I read a base 10 number and store it into X? If not, get out of the loop, the rest doesn't matter anymore. If I did read a number and store it into X, now it's time to see if that number is different from 0. As long as I keep reading numbers and they are not 0, I'm stuck in this loop because this condition, this conjunction stays true the entire time. Am I making any sense? As long as I keep reading base 10 numbers that are non-zero, the conjunction as a whole remains true, so I will be stuck in this loop. I can get out of this loop using two different ways. One is to specify a non-number, like ABC, the pound sign, anything that cannot be interpreted as a base 10 number. That will make scanf return a 0 because I cannot interpret those characters as a base 10 number. That's one way to get out of this program. The second way to get out of this particular loop is to specify a 0, because in that case I would have read a number. This would return true. However, this would be false because if x is 0, then x is different from 0 is going to be false. True and false is false, so I will still get out of the loop. So are we doing okay so far with understanding what this code is supposed to do? Well, if that is what it's supposed to do, let's try it out and see whether it does what we think it should do. So I'll just go ahead and retype this program into the editor. Okay, that's fine. I'll just call this scanf.cpp. So we have the program typed in. Let's go ahead and compile it. The compiler will most likely complain about it. So let me see if you can read this program and tell me what the compiler is going to complain about. The syntax is fine, okay, because the compiler will only warn about certain things. The syntax is okay, there's no problem with the syntax. But it will find something that is kind of fishy about this program and complain about it. What do you think the compiler will find kind of fishy?
That there's
Say again? Nothing is inside the open and closed curly brace in the while loop. That's actually okay. The compiler does not complain about that one. What am I doing with x other than putting a value into it? Nothing. Okay, so the compiler may complain about that one. Some compilers will not complain about it, but we'll see. It depends on how well the compiler understands scanf. And in this case, scanf Oh, dash O, forgot about the dash O. And it did not complain about it. So to the compiler, it is okay to basically specify the address of X without using X later on, because that can potentially be using X. Okay, I can kind of understand that. But let's go ahead and run the program. When we run, scanf, it's waiting for me to type something from the keyboard, because after all, with anything that makes use of the standard input file, remember what is the default standard input file?
The keyboard?
The console, the keyboard. Okay, so unless I redirect the input from a file, from some actual file, the shell, which is bash in this case, will basically say, oh, okay, you want to specify the keyboard as a default for the standard input file, and that's why it's waiting for me to type something. If I type 4 and press the enter key, it actually would store 4 into X, and and then it reads again because the loop doesn't do anything with the value of X. I can specify ASDF, and that is not a number. Okay, so at this point, when I press the enter key, scanf will try to look at the character A and say, can that possibly be the beginning of a base 10 number? And the answer is no. And because the answer is no to that question, scanf returns 0 to basically mean I was asked to read a base 10 number, and this cannot possibly be the beginning of a base 10 number. So it returns a 0 to means it could not read what I was asking it to read. And then because the left-hand side of the conjunction failed, the entire conjunction is going to return false. We get out of the loop, the program exits. Okay, so when I press the enter key, it gets out. Now let's try something else. What about 5 minus 5? That's a tricky one. It's a tricky one. This is kind of like a doubly or triply tricky one. Okay, so the first question is, do you think the program is going to exit?
Yes.
I say no.
Okay, so the answer is the program is not going to exit. Okay, because even though to us 5 minus 5 is 0,
It just sees 5.
scanf does not evaluate the operator. So what scanf is going to do?
So what happens when it sees it on that second iteration?
Say again?
So what happens when it sees it on that second iteration?
That's a good question. The second question is, how many iterations will this force the loop to go through? Okay, so we'll answer both of those questions. The first question is, so how is scanf going to interpret this particular input, 5 minus 5? So the first thing is it will see 5, right? Is 5 a valid beginning of a base 10 integer? Yeah, that's cool, no problem. So then it will, remember the input file is a conveyor belt. So once we process the first 5 character, the digit 5, it's going to move on to the negative symbol, okay? Is 5 minus a good representation of a base 10 number? No, so it will stop right there. It will stop right there and say, okay, I can see that 5 is the integer. This minus probably belongs to somebody else. I'm not going to worry about it. So right away, it will return a 1. Scanf returns 1 because it has successfully interpreted 5, the digit 5, as the value 5. Store that into X and return a value of 1. 1 equals 1, no problem with the left-hand side. So we move on to the right-hand side of the conjunction. X would have a value of 5 at that point. 5 is different from 0 is
True.
true. So now we have true and true, not a problem. The loop goes back to the beginning, and it will go for a second call of scanf. So when we are starting with a second call of scanf, the first character it's going to read is the leftover from last time, which is a minus symbol, the negative symbol. Can a signed integer start with the negative symbol?
Yes.
Yep, because that's how you specify negative numbers, right? So scanf says, okay, I can see that this is going to be a negative number. Move on to the next one. Oh, it's a digit. So negative 5 is perfectly okay as a signed number in base 10. And then scanf will try to interpret the line feed character. The line feed character is kind of like a spacer, right? Okay, it's only there to separate numbers. So scanf would say, okay, that's not a part of a number, but I'm going to parse and get rid of it anyway. But at that time, it would have read -5 as a value. Store that to variable x, return a value of 1. That one, the value of 1 that scanf returns compares to 1, 1 equals 1 is true. That's the left-hand side of the conjunction. The right-hand side of the conjunction will now be evaluated. -5 does not equal to 0 is true. So we have true and true, which means the entire conjunction is true. Now it will go back and try to read again. The third call to scanf. So let's press the enter key, and all we can confirm is it does not get out. It doesn't really quite indicate this is the third time we call scanf, but the explanation that I went through is actually correct. There are ways you can actually test this program by setting up breakpoints and evaluate what x is after each iteration. Right? Any questions about what just happened? No questions? Okay. So if there are no questions, I'm going to put a 0 here and just end the program. Oh, what about 056? Would that be okay? How many times scanf is going to process this, and what is going to happen to x?
Well, the first time, wouldn't it pick up on 0 and then it would be false?
It's greedy. It will try to read as many characters as possible and still be an integer. So 056 is a valid base 10 number. So we actually read the entire thing up to the line feed character and then put it into x.
Would it put 056 or just 56 in there?
Internally, it stores the value of 56 in binary. So I'm not going
So it doesn't
to
matter.
say how it's going to print it because we don't have any print statement. Now, if we did have a print statement, then you can control how it is going to be printed. So are we still doing okay so far with this program? Is that okay? All right. So if you're okay with this program, we'll go back to the browser. The rest of this slide is really just a typed up version of what I just said. Okay, so there's really not much else to the rest of this text here. The big question is, hey, this is the first time we see something like that. Okay, we have seen a single ampersand between two values. That is the bitwise AND operator. But then single ampersand only on one side of a variable, this is the first time we see it. So what it means is it is the address of something. So now we have to kind of talk about what is the address of something, what is an address, and what is a pointer. And that's kind of a big topic in C and C++ programming, and somewhat differentiates C and C++ from other programming languages. Java does not have pointers. Perl doesn't have pointers. Python has no pointers. PHP has no pointers. Visual Basic has no pointers. Okay, so out of almost all of the high-level programming languages, C and C++ is the only one that has pointers. So what I'm going to do is I will move on to pointers, and start with this slide here. So we'll kind of go crisscrossing a little bit here. We'll start with pointers and then kind of go back to Cin in the next class. So at this point we have the first contact with pointers. And to understand pointers, let's not read this stuff here because it's kind of boring, it's all text. So instead, what we'll do is we'll kind of imagine that we are working for a mailbox, company, okay, or USPS, with a post PO box, okay. So with PO boxes, let me find my dry marker here. This part is mostly about the concept. I don't really think you need to write down anything. Just kind of focus on what I have to say. Okay, so let's say out of a particular branch of the post office, it has a certain range of PO boxes, and PO boxes, they do not have to necessarily start with 1, right? But they can start with, let's say, 500, 1,000, right? So let's say in this case we start with 1001. That's the first number of the first PO box. 1002, 1003, and 1004, and so on. Okay. One thing about these PO box numbers is they are sequential. Okay, you cannot skip numbers. They are not randomly organized. They are completely sequential. What can you put into a PO box?
Mail.
Anything that fits in that box, right? Okay, so that's good. You can store any content that will fit within a mailbox. So let's just say that one day, let's say I had PO Box 1001 to begin with, okay, and then one day I decided I don't like this particular PO Box number. I want to use PO Box 1004, okay, and to remind the person who's going to put stuff into the mailboxes, this time I'm going to leave a note here and say go to PO Box 1004. In other words, for the person who got stuff that was originally intended for box 1001, this little instruction is saying, oh, don't put it here, okay? Put that over here instead. Is that okay? That's the concept of an address.
Well, you said whatever will fit in the box. How much data can fit in one of these?
Well, in this case, it's kind of physical, right?
Yeah.
Whatever the size of the box is. But the little slip of paper that says go to number 1004 would certainly fit in the box.
Oh yeah, no, I'm saying if we're trying to store things into this, what is there a limitation as
Yes.
to how much? That's what I'm asking.
We'll get to that part. We'll certainly get to that part. But this is the concept of a pointer. A pointer is nothing more than a way to find something else. Okay. So in a way, call numbers that you use, to find books in a library, that's kind of like an address because each call number can help you find a book uniquely. Okay, that's kind of like an address. Are we doing okay so far with this example? Computer memory is kind of organized pretty much the same way, except as you asked, how big is a box? Now, how big is a box is kind of a tricky question. One box in memory is 8-bit for most processors. 1 bit, remember, is one binary digit, a 0 or a 1. So 8-bit is basically just 8 zeros or 1s, kind of packed together. It's also called a byte, okay? B-Y-T-E, byte. So one thing that you can address using the processor is exactly 1 byte, and that's why most architectures is also called byte addressable. Is that part okay? Okay. So now that we know the smallest unit we can address using most modern processor is 1 single byte, what about the address of these bytes? The address of a byte is nothing more than a big number. Okay? With a 32-bit architecture, an address can be a 32-bit number. And how many locations, how many different addresses can you have out of 32 bits?
2 to 32?
2 to the power of 32, which is approximately
A lot.
approximately a lot. Approximately 4 billion, okay? So with a 32-bit architecture, the processor at any time can specify 1 out of 4 billion addresses, approximately 4 billion addresses, and say, I want to access that byte over there. And it can pick 1 out of 4 billion or so. Is that okay? Okay. So then we want to say, okay, but exactly what is an address? Well, an address is nothing more than a binary number with a 32-bit architecture. Is 32 zeros and ones strung together. That's an address. So it is not unlike a number. It really is a number. An address is essentially a number, but there are limitations. Out of the entire 4 billion locations, so let me just kind of draw this out, and we'll just say that this is 0, and this is F, 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 F in hexadecimal, okay? So in hexadecimal, F, 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 F is the largest number you can represent, about 4 billion something in decimal. Is that okay so far? So this is the entire range of memory locations out of a 32-bit architecture. Out of this entire range, a program that is in execution will only be allocated a small chunk of this. So you will have basically a little chunk here and maybe a little chunk here that is allocated to your program. Okay, wait, hold on a second here. I thought programs are stored on hard drives and CD-ROMs. You know, how does that have to do with memory? Well, there are two different states to a program. When you store a program, which is just a regular file, it is on the hard drive. So let me show you exactly what I mean by that. We just created some of these programs a little bit earlier. Scanf, okay, ls-l scanf here. It is a file, okay? It's a program that can run, but at this point it is a file. Now when I run a program, okay, using /scanf, the file is still on the hard drive. But in addition to the file that is corresponding to the executable of this program, I also have an instance of this program that is currently in execution. Can everybody kind of distinguish these two terms? A program that is stored on a hard drive and say, you can run it whenever you want to, as opposed to a program that is in execution. It is being run right now, which is scanf. Is that part okay? But I can do something like this too. With this program, scanf already running in this terminal, I can open up a new terminal and go to the same folder and say, hey, I can run the program again. So out of the same program, you can run it, it can have any number of instances that are running at the same time. And that's really kind of awfully confusing because now we're looking at the same program that is stored on a hard drive, which is only one, okay, there's only one file called scanf. But now I have two instances of that program in execution. And that's why we come up with the name process. A process is an instance of a program in execution. Is that okay so far? I can give you an analogy, and I think that will clear up everything. I'm just looking for a prop here. Okay, this is going to work. Okay, a program is nothing more than a folder, a binder that has instructions in it to tell people what to do. It's just one single binder. Okay, so when it is stored on a hard drive, it is basically the same thing as I put a program in my folder. Is it doing anything? No, it's just keeping its own state. I'm not losing the content of that file, but at the same time, it's not doing a single thing. So what is a program in execution? What is a process then? A process is a person getting this file, basically a copy of it, okay, because you have to leave the original here. So it's one person going to this thing here, make a photocopy. Unfortunately, the printer is all the way over there. I cannot use it as a prop. But basically, when you run a program, this is what happens. A person, which is the processor, okay, taking the program from the folder, run it through a copier, put the original back here, take a copy of the file, and then start to follow the instruction to do something. That is a program in execution. Now, using this analogy that you have to make a photocopy of the original instruction to run it, to follow the instruction, is it possible for someone else after me to do the same thing while I'm still running that executing those instructions? Yeah, the only limitation is when are we going to run out of paper from the photocopier, right? Which is basically translating to memory. So every instance that is running a program is going to consume some memory. And you can run the program like scanf here. We can run it as many times as we want concurrently until we run out of resources. And that's perfectly okay. When we look at one single instance or one single process, to that one single process, it has a memory range that goes from 0 all the way up to 4 billion something for a 32-bit architecture. For a 64-bit architecture, it is a much larger range, but it's just a matter of size. The concept is still the same. Out of this entire range of addresses, the process only has read-write access to a very small part of it. So in this particular case, I only have access to a small portion, which is the one part that I have highlighted here. I have this part that I have access to. I have this part that I have access to. So one part will correspond to the instruction manual itself. The other part will correspond to all the variables, which is kind of like a notepad that I need in order to get my job done. I have to kind of write down something and erase it and write down something again. That's the data portion. Is this still doing okay? So when you magnify a particular portion like this, it is basically a sequence of bytes. Okay, it is basically just a sequence of bytes here. Each one has its own address. So each byte has its own PO box number, if you will, to distinguish it from all the other bytes within the memory space. Are we still doing okay so far? And these bytes are sequential, which means if this is location, I'm going to use base 10 as an example. So if this byte location is, let's say, 20,631, then the next one is going to have the address of 20,632, and this is going to be 20,633, and so on. So memory can only be sequential and contiguous. You cannot skip around and say, oh, I want to jump by 10 bytes and go all the way over there. Cannot do that. Are we still doing okay so far with the layout of memory inside the computer? Any questions?
So what happens if you're running the same program in two instances? How does it know to separate the?
That's a very good question. When you run the program, you need two things. When you run a program, you have a copy of the instruction manual, and then you have a binder, so that you can basically let's say your job is to find out of the library which book is the thickest, okay, out of an aisle, okay. So you need to kind of keep track of the thickest book that you have seen so far, and that's basically on a different book. So you have two binders, one to tell you what to do, and the other one will store the data that you need to keep track of in order to get your job done. Is that okay so far? The tricky part is, if I run this program again, the layout is going to be the same. In other words, the first program in execution, the first process, has a location 2631. The second program also has its own location 20,361. And so how does that work out? This is because with modern processors and modern operating system, to make use of those features, it's called protected mode program execution. So each program, each process has its own quote-unquote memory space that is independent from the memory space of any other process in the program. It's an illusion. Okay, obviously we don't have 4 gigs of RAM to allocate to each program that is in execution. But as far as the process is concerned, that is its range of addresses. But out of the entire range, only a small portion is accessible. If you try to access locations outside of this range, you will get what we call a segmentation fault. The processor will enforce that rule and say, oh, you can only access from here to here and then from here to here. If you try to do anything else, the processor will basically come back and say, can't do that.
So they still technically would have the same address. So like, let's say the executable that you ran here, let's pretend that its address was 20,361. Both instances have the same address?
Yep. Now, we don't have to we can actually demonstrate that part too. So the way we demonstrate it is we run it through GDB. And did I compile it with, no, I forgot about the -G, so I have to recompile using -G to include, I said G, not F. Okay, GDB scanf. Put a breakpoint on line 6, and on the other side, I would do exactly the same thing. Okay, so I'm going to GDB scanf, put a breakpoint on line 6. In each one, I run the program. And we run the program on this side. So now we have 2 programs or 2 processes that are coming from the same program, and they have stopped in the debugger at exactly the same spot. Okay. So now the question is, out of these 2 processes, is X at the same location? In other words, what is the address of X? Is it the same thing? That's the question. Well, first of all, what is the address of x? How do we refer to the address of x? If I just say printf, it is the content or the value of the variable x. So how do we get to the address of that variable? Not the content, just the address.
Well, the address is the single ampersand. So.
A singles ampersand, very good. So we say singles ampersand x, that would be the address of x. So in this case, the address of x is some really kind of funky, value here. This is in hexadecimal because it starts with 0x. So the location is BFFFA3C, which is approximately 2/3 through the entire memory space. Okay, that's kind of approximately where it is located. Okay, so let's remember this number. I'm going to put it over here so that we can see at least this part here. And we'll do exactly the same thing with the other process. So we'll say, hey, with this process, where's x? What do you see?
Same thing.
They are exactly the same. It's kind of like having two workers following the same operation manual. And in the operation manual, it says, oh, flip to your data logbook on page 500 and do blah, 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 blah. Is that a problem? It's not a problem, right? Because the first worker and the second worker, they have a different logbook. So when we say flip to page 500, to the first worker, it is page 500 of his or her own logbook. The second worker has an entirely different logbook, so even though it is still referring to page 500, it's a page 500 of a different logbook. And that's what's happening here. Are we still doing okay? Kind of? All right. Okay, now we have a second question. The second question is, what is a 32-bit integer? Well, a 32-bit integer is an integer that requires 32 bits to represent. Wait, a byte is how many bits again? A byte has 8 bits, okay? And we have integers that require 32 bits to represent. So how does that fit into this scheme here? All it means is a 32-bit integer needs 4 bytes to represent. Is that okay? So if I want to store a 32-bit integer into memory, it will take up 4 spaces or 4 bytes. So we'll just say that, okay, let's say that we have x, and it will take over these 4 locations. 20,634. All right. There are 2 rules you have to remember. One, you cannot break up an integer and say, I will put 1 byte over here, 1 byte all the way over here, 1 byte over here, and then the last byte over here. The 4 bytes of a multi-byte variable must be stored in contiguous memory. They have to be right next to each other. Which kind of makes sense, right? The second thing is, when you refer to a variable, the address of a variable refers to the address of the byte that has the lowest location. So in this case, this particular variable x is taking up these 4 bytes. So what is the actual address of variable x? It is not the entire range of number. When we talk about the address of x, we are only referring to the address of the first byte of the multi-byte variable. So in this case, 20,631 is the address of variable x. Is that part okay? All right. If that is okay, then we're going to move on, and I can kind of show you where we are at this point. So we are already done with the address of operator. So we are ready to move on and talk about how do we store the address of a variable. Okay, if we can extract the address of a variable, in this case, variable x has an address of 20,631. So if we can extract 20,631, which is the ampersand operator, what can we do with it? Well, the first thing is we can store it. We can put it somewhere. Okay, which is kind of the same thing as the first example that I used. Putting a slip of paper in one of the PO boxes so that we can look at that piece of paper and say, oh, okay, we have to go to PO Box 1004 to actually do something about it. So that would turn Box 1001 into what we call a pointer. A pointer is a variable that contains the address of some place. And sometimes it can be the address of itself. It's not very useful, but it can be done. Okay? In other words, you can say 1001 and put a 1001 here also. So an address can be, a pointer can have an address of itself. Because after all, an address is just a bit pattern. It's just a 32 zeros and ones that can identify the location of a byte. Are we still doing okay so far with this discussion? Sort of? Okay, this is kind of like a big topic. We'll come back to this again. But I do want to give you an early exposure to kind of give you some time for this stuff to sink in, and then when we come back, we'll add something else to it. Okay, so there are variables that can store the address of variables, even that of itself. These variables are collectively called pointers. So when we talk about a pointer, it is nothing more than a variable that can store an address. A pointer variable is declared using the asterisk symbol. So the entire declaration is this. The way we say what is int asterisk p int is to read it backwards. Okay, so this part you might want to write down or kind of keep track of it. We say p int points to an integer. That's all it says. Which integer? This declaration does not say. It is really just saying that, you know what, this little slip of paper is supposed to be a call number. Well, without actually looking at the little slip of paper, do you know which book's call number is on this paper? No, we don't. We don't even know whether it's a valid call number. We just says it's the intent, okay? This piece of paper is intended to store a call number. That's all that this is saying. So this is basically just saying pint is supposed to store the address of an integer. Is it really storing the address of an integer? Don't know. Okay? We're just saying what it is supposed to do. We are not saying that it has an address of an integer. So to make sure that it does have an address of an integer, just like with any other variable, you have to initialize it. Okay? So in this case, the highlighted part here says pint is now the address of x, or it stores the address of x. Are we doing okay so far with that concept? So first of all, we have the concept of an address of something, because every variable is occupying some bytes in memory, and each byte has an address. So every variable also has an address. So that's the first concept that we talked about today. The second concept is the ampersand operator. To us, the programmers, the symbolic name x is easier to remember than some kind of long-ish address. But in some cases, you need to get the address. So to get the address from a variable, you use the ampersand operator, which is called the address of operator. What can you do with an address? Well, you can use it in scanf right away. But you can also store the address of something into what we call a pointer. A pointer is a variable, but it doesn't store a value. Instead, it stores the address of something else. When you declare a pointer, you're basically just saying pint is intended to store the address of an integer. It doesn't really necessarily store the address of an integer. To make sure that it does, you need the initialization. Just like with any variable, when you declare a variable, it is uninitialized. It has a value, but we don't know what it is. You have to initialize it so that it can be used later on correctly. Now with pointers, it is particularly important to initialize before you make use of the pointer, because an uninitialized pointer can point to La La Land. Okay? Now it is a good thing when it points to La La Land, because when your program tries to make use of a pointer that points to La La Land, it will just give you a segmentation fault, bomb out, and just say, can't do anything about this. That's a good thing. So what is a bad thing? A bad thing is when the pointer points to a location that your program, your process actually has access to. So parts of your program, a part of your program can corrupt the memory of another part of the program. In other words, one part of the program can make accidental changes to variables that are used in elsewhere in your program. The program is not going to bomb out right away. Instead, it will continue execution as if nothing bad has happened until it gets back to the code where the corrupted location is utilized. Then it might have symptoms. So by the time you have the symptoms, you can be millions of lines of execution away from the cause of that problem. That type of bug is very difficult to catch because by the time something shows up, you're so far away from the origin, from the reason why you had that problem to begin with. So that's why when we use pointers, we have to be extra careful because they can lead to problems that are not easy to debug even with GDB. Because the symptom shows up much later. It's kind of like a time bomb thing, except it's even more random. It's not like, oh, this is going to go off in 5 hours. It's more like, it'll go off when it feels like going off. So that's why, when we deal with pointers, we have to be careful. We are running out of time today, so I'm going to stop here. When we return on Wednesday, we'll finish up cin, which is the other way to get something out of the standard input file, and then we'll move on and talk about pointers, kind of like full strength at that point. All right, so I'll see you guys on Wednesday. There are no homeworks at this point, no active homework. I forgot to take rows, yes.
I think on the what was I gonna say?